Okay, welcome back to Chapter 9 in Stat 218. Chapter 9, Section 4 is a very different approach than Chapter 9, Section 2. And so, if you skipped the Chapter 9, Section 2 video and then skip the problems, that's fine. They're very different in their nature. You could jump right into Chapter 9, Section 4 and do the problems in 9.4 first, and then go back and do the Chapter 9, Section 2 problems. So in Chapter 9, Section 4, we're dealing with the chi-square approach and my very favorite pie chart, the pie chart of mystery. 41% orthopedic shoes, 28% artisanal cheeses. Yeah, like that fits. 11% non-reactive matter, 4%, what does that even say? I can't even read that. And then 16% people who earn over $100,000 per year. Just let's take a collection of categories that don't really fit together and make a pie chart. That's why it's my favorite. Okay, so I'm going to sort of get into a question about population proportions, and it's going to sort of get us towards chi-square, the Chapter 9, Section 4 approach. If I flipped a coin 100 times, you'd think you should get 50 heads and 50 tails. What if I flipped a coin that was somewhat unusual in its look? It looks like it's maybe from a foreign country or maybe not even really a coin that could ever be spent anywhere. Half those foreign country currencies, they look like coins, but I don't know. If it's from Botswana, I don't know what the Botswanan coins look like. So someone hands you this coin, you flip it 100 times, you get 40 heads. Would you believe the coin is biased? I'm thinking this has got to be a hypothesis test, because I'm saying, is the coin biased or not? Is the coin biased? Is the natural alternative hypothesis coin is biased? P is not 0.5. The null hypothesis corresponds to no bias. The value for P, the rate of heads, is 0.5. A confidence interval like previous Chapter 9, Section 2 could help us. If our confidence interval for the rate of success, the rate of heads on the coin, includes 0.5, a fair coin, 50% heads and 50% tails, would not be viewed as unusual or surprising or implausible. So the confidence interval may help us answer the question, but if you want to formally test a hypothesis, you're thinking 40 heads and 100 flips, it's hard to know. If I asked you about 48 heads and 100 flips, you'd say, oh, that could easily be fair. If I said 15 heads and 100 flips, you'd say, oh, no way is that a fair coin. 40 seems like it's maybe on the outskirts of what's reasonable to believe. Okay, so our null hypothesis, the coin is fair, 0.5. The rate of heads, which I'm going to call P for now, the rate of heads, P, is 0.5, or it's not, in which case the coin is biased. And that either means favoring heads, in which case P is greater than 0.5, or favoring tails, in which case P is less than 0.5. Our test statistic is always a measure of how different the data are from what the null hypothesis suggests the data should be if the null were true. We actually did get 40 heads and 60 tails, but you would expect 50 and 50. So in our equation here for this chi-square statistic, x squared, not really x, chi squared, think Greek organizations, chi squared. O was the observed count. I got 40 heads. I expected 50 heads, square that difference over the 50 heads, and I got 60 tails. I expected 50 tails, that difference squared over then the 50 tails I expected to get. We're summing across both categories. We're summing across all categories. So again, observed minus expected squared over expected, 40 minus 50 squared over 50, plus then 60 tails minus the 50 that I would have expected to see squared over 50. I get a chi-square value of 4. So let's think it through in terms of what if I had 50 and 50? If the observes and the expecteds were exactly the same, if O was 50, 4 heads, and 50 for tails, but I expected 50 heads and 50 tails, the numerators would all be 0 squared. My chi-square value would be 0. The chi-square value is small when the null is true. What if I had 100 heads and 0 tails? I'd have 100 minus 50 squared over 50. And I'd have 0 minus 50 squared over 50. My chi-square value would end up being actually 100. So the smaller chi-square is, the more closely the data match the null hypothesis. The larger chi-square is, the more closely the data match the alternative, or the further the data are away from the null hypothesis. So hypothesis test steps. Null and alternative hypothesis, calculating chi-square. Next step is always that p-value. So I'm going to recommend using a chi-square table because it's the chi-square method. There's 2 different sources of a chi-square table, page 686 in your textbook, or I've got one online for you. The handout is on the class website, and let's make this larger so we can read it. Over here off to the left, your chi-square value for, like before, like with the t-table, we could find for the right degrees of freedom the chi-square value, bracket, and read to the top. Okay. So what is the degrees of freedom? I'm just saying for chapter 9, section 4, the number of categories we have minus 1 will be degrees of freedom. In chapter 10, that approach to degrees of freedom will be incorrect. It's another approach to degrees of freedom we will be choosing. But we got heads and tails here in chapter 9, section 4, 2 different categories, 2 different levels of the categorical variable, 2 different categories minus 1 gives us 1 degree of freedom. So 1 degree of freedom, and my chi-square value was, again, 4. So let's look on our table in the 1 degree of freedom row and look for a value of 4. And in this 1 degree of freedom row, 4 would appear here. It's somewhere between 3.84 and 5.41. So my upper tail area would be somewhere in the range 0.02 to 0.05. My p-value is thus in the range 0.02 to 0.05. Now, with that p-value in the range 0.02 to 0.05, it's strictly less than 0.05. My conclusion is this coin is biased. The null hypothesis of fair coin is rejected. The null of the coin being fair is rejected. We saw data, the 40 and 60, which was different enough from the fair case, 50 and 50, that we say our data substantially or statistically significantly different than the null. So this goodness of fit test, if you will, in chapter 9, section 2, could be used for other situations as well. I'm going to tell you a brief story about a guy named Joseph Jagger, the man who broke the bank at Monte Carlo. The Rolling Stones wrote a song about him in the 1970s. And turns out that he, in the 1800s, late 1800s, in July, went to Monte Carlo, okay, with a few bucks. Well, okay, he was British pounds, but he converted it to Monte Carlo francs at the time, and then sits down at a roulette wheel and watches and watches and watches and watches and watches. Actually, he observed all of the roulette wheels, every single outcome he recorded. And he noticed that certain numbers came up more often than others. 7, 8, 9, 17, 18, 19, 22, 28, and 29 came up a lot more often on one of the tables than he would have expected. So he starts betting a lot, wins a lot. And the casino notices this guy who sat there for a full week taking down data. Then he comes in and starts betting and winning. They figured, okay, this is a problem. They swapped tables on the guy. Literally overnight, they picked up one table, the table where he usually would sit. They moved it next door to the next slot over, and then the one that had, they just swapped two tables. He goes in, sits in the one seat he had sat in the previous day, and starts losing. And he looks down and sees that the scratch on the table leg where he normally would sit was missing. He gets up, walks around. Oh, there's my table, sits down at that table, which he knows is the good one, spends the rest of the day winning money because he's betting on the numbers that come up most often, those guys. And then the casino, at one point in time, they say, you know, this is just bad. This one table is not helping us. They took it off the floor entirely. He walks in the next day, looks around, sees that the table he had been betting on is no longer there. So he gets up and leaves and went back to England, $5 million richer. For 2 weeks of work, $5 million is not so bad. So here's how he pulled it off. Where are the numbers that came up? 17, 18, 8, 9, 10, no, 7, 8, 9, 17, 18, 19, 22, 28, and 29. I've circled them here. You're sort of thinking maybe those, it's just luck that's causing those to come out a little bit more often. But these over here, it seems as though, to quote a past student, the the northwest side of the wheel comes up most often. And I can't deny that. So he'd go in and he'd say, I'm going to put 10 pounds there, 10 francs 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 there. And if on any one of these numbers, if he gets it, the bet, they hand him back his 10 francs for the number that he, suppose 7 came up, he'd get the 10 francs back, plus an extra 360 francs. So you bet 10, 20, 30, 40, 50, 60. And if any of these numbers came up, he basically lost 50 francs, but got back 10 that he had bet, plus another 360. He was up 300 some francs if any of these numbers ever came up, and they came up often enough that he did end up doing quite well. Essentially, the method that he was using was similar to a chi-square test, where he said for each of the various possible outcomes, the 36 pockets that the roulette ball may end up in, they each should come up with a rate of 1 in 36. Same thing as with our friend the coin. The coin that's fair should come up heads half the time, tails half the time, 0.5 and 0.5. With roulette, 1 in 36 is the chance for any one of those pockets. And so the null hypothesis is all of the possible outcomes have chance 1 in 36. It's a composite null hypothesis because it's talking about more than just one possible outcome. Every single one of the 36 different pockets comes up just as often as the others do. The alternative hypothesis, at least one of those rates is not 1 in 37. I could calculate the number of times I got a 1 compared to the number of times I should have gotten a 1. Square that over the number of times I should have gotten a 1. For a 2, 3, 4, 5, 6, all the way through 36, plus then the green double zero spot. How many green double zeros did I get compared to the 1/37th of the large number of rolls I observed? Square that. Well, that's easy to do. And you'd say 37 different possible categories, 36 degrees of freedom. We're not going to do that because that'd take way too long to sum across 37 possibilities. We're going to talk about Gregor Mendel and his P's. Now, many of you have been in a bio class where you've heard of Mendelian genetics or the Punnett square or those sort of fun things. I'm saying my story is approximately close. I've had students who say I'm close enough for, to illustrate the method. But Gregor Mendel, let's suppose he bred a collection of plants that were pure hybrids that were yellow seeded, smooth seeded plants. And then he's got another group of hybrid or purebreds that are green seeded, wrinkly plants. So yellow smooth, wrinkly green. In the first generation of hybrids, okay, all of the first generation hybrids should have one gene from each mom and dad plant. We should see smooth yellow seeds because smooth and yellow are both dominant. Okay, but in the second generation, the first generation crossbred with the first generation, we're going to end up with 9 out of every 16 plants should be smooth and yellow. 3 out of 16 should be wrinkly and yellow. 3 out of 16 should be smooth and green. 1/16 should be wrinkly and green. And if you're wondering where you get these numbers, I refer you to your bio textbook. But because smooth is dominant and yellow is dominant 3/4 of the time, you should have each of those. Multiply them together, you get 9/16. 1/4 is the rate of wrinkled seeds because it's recessive. 1/4 is the rate of wrinkled seeds because it's green. Okay, 1/16 overall is that rate of the wrinkly green plants. So 4 possibilities in terms of the way they look, their morphology. Let's see how often we got each of the different types. 556 plants in total. I had 313 smooth yellow, 104 wrinkly green, 104 smooth green, 35 wrinkly green for my 556 plants in total. How many would I expect of each of the different 4 morphologies? Of the 556 plants, if 9/16 were smooth and yellow, 9/16 of 556 is 312.75. I would expect that number of smooth and yellow. I actually got 313, pretty close to 312.75. For wrinkly yellow, 3/16 of 556 is 3/16 of 556, 104.25. Wrinkly yellow, 104.25. Smooth green, 1/16 of 556 or 34.75. Wrinkly green. My chi-square value is something across all 4 different morphologies, different ways of looking as a pea plant. 313, the actual count compared to the observed of 312.75 squared over 312.75. 104 minus 104.25 squared over 104.25. Same thing next door for smooth and green, the actual count of smooth green and the number I'd expect squared over then the expected number of smooth green. And finally, the 35 wrinkly green, I expected 34.75 of them, so I square that difference and then divide through 34.75. My chi-square value is really small. By the way, whenever I see a chi-square value that is exceptionally small, like this one is here, I always double check to make sure I didn't have a parenthesis around the difference and then the division before I square. You square first, then you divide. If you get a tiny value for chi-square, either you did it right and the data really closely match the null hypothesis, or you have a situation where you maybe did a calculation error. And again, the most common calculation error is the dividing before you square. So with 1, 2, 3, 4 groups, I've got 3 degrees of freedom. My chi-square value is tiny. Let's look at my chi-square table. 3 degrees of freedom. Where am I going to find that? 3 degrees of freedom. In that 3 degree of freedom row, which I'm underlining here. If I were to see 0.003, it would be certainly to the left of even the leftmost values I have in my table. Thus, my upper tail area must be greater than 0.2. Notice as I move to the left, the table areas get larger and larger and larger. My p-value is greater than 0.2. I can live with that because I know what to reach as a conclusion from the p-value being larger than 0.2. My p-value is larger than 0.2. My conclusion thus is we cannot reject Gregor Mendel's hypothesis as not matching the data. The data here that we did see pretty closely matched the observed or the expected counts. Lastly, M&Ms, the last example, M&Ms. Mars, M&Ms, they claim to have 30% brown, 20% yellow, 20% red, 10% each orange, green, and blue. In a bag of M&Ms, I found 85 brown, 79 yellow, 75 red, 49 orange, green, and 47 blue. Was the company lying to me, or were they telling me the truth about the number of each variety? Let's see what we get. Now I'm going to sort of work over here on the right and state my null hypothesis. The null hypothesis is always with multiple key categories. It's always composite and always has a collection of equalities. My null hypothesis is that the rate of, well, let's go brown, PBR equals 0.3, PY equals PR equals 0.2 red, and then P comma P orange equals P green equals P blue, BL for blue is 0.1. 371 M&Ms in total. How many would I expect of each of these different colors? So the null hypothesis right there, alternative HA, not that. At least one of those rates is not the same as the stated here. So the expected counts correspond to the null hypothetical rates and 371. So the expected count of blue, so the expected blue, BL, is, well, 10% of 371, 37.1. The expected number of green is 37.1. The expected number of orange is 37.1. The expected number of red equals the expected number of yellow equals 74.2. 20%, 0.2 and 0.2, 20%. Oh, and then, yeah, 20% of each, 371. And then finally, for brown, the expected number of brown is, well, 3 times 37.1. So that is something 0.3, 111.3. Did I get it right? Okay, so 40, yeah, 111.3. So I have my expected counts right there, and I've got my observed counts here. My chi-square value is 13.025 with 5 degrees of freedom. What do I hit as my conclusion? 5 degrees of freedom. My chi-square was 13.025, 13.025 with 5 degrees of freedom is somewhere between 13.025. It's somewhere between 0.02 and 0.05. I think I got that quite incorrect. I cut that in half due to using a different chi-square table. But if I said 0.02 to 0.05, you would have the conclusion that you believe the alternative. These M&Ms are not matching the claimed percents according to the company's website. The company says, here's what we put in the bags. What we saw put in our bag differed noticeably from their claim. So either our bag was a bummer of a bag, or perhaps, on the other hand, maybe they're lying to us. It's the only two possibilities are those two cases. Okay. Last thing to do is to, nope, that's it for the day. We will see you next time when we will finish up. Well, we'll start in on chapter 10 next time. So stop the recording. We'll see you soon.